Hello everyone, I'm going to be talking today about some work done jointly with Anuj Dawar on symmetric arithmetic circuits. So in particular I'm going to first introduce a natural notion of a symmetric arithmetic circuit and then show that in this model we can separate the permanent and the determinant. So firstly that means showing a polynomial upper bound for the determinant in this model and a superpolynomial, almost exponential, lower bound for the permanent. So let's begin with some basic concepts in arithmetic complexity. So in arithmetic complexity, we're interested in representing or computing polynomials. And the computational model we use to do so are arithmetic circuits. An arithmetic circuit is defined over some field. It's a DAG structure. It has input gates labeled by variables and field elements, and internal gates labeled by plus or times. And such a circuit naturally represents a polynomial. There are two complexity classes of particular interest. The first, VP, which we should think of as analogous to P, and the second, VNP, which we should think of as roughly equivalent to NP. And perhaps unsurprisingly, Valiant's conjecture asks whether these two complexity classes are the same, and indeed he conjectures they're not the same. And we should think of this as the analogous algebraic conjecture, the algebraic analog of the P not equal to NP problem. In arithmetic complexity, there are two families of polynomials that are of particular interest, the permanent and the determinant. The determinant, I expect, is already very well known to everyone. But here we think of the determinant as in a family of polynomials indexed by the natural numbers, where the nth such polynomial is the determinant of an n by n matrix of variables. The permanent may be less familiar to some people. It's also a function on matrices. Here again, we think of it as an infinite family of polynomials, where the nth such polynomial is the permanent of an n by n matrix. For those who haven't seen this before, it's perhaps striking that there's such a small difference between the two. In the determinant, we have this sign sigma floating around, but otherwise they look very similar. It's perhaps surprising then that the permanent turns out to be complete for VNP, under polynomial projections, and the determinant complete for VP under quasi-polynomial projections. As a result, Valiant's conjecture is equivalent to proving a superpolynomial lower bound on the permanent, and indeed we often think of this conjecture in terms of this difference between the permanent and the determinant, this apparent difference in difficulty between the permanent and the determinant, which is sort of the central question in arithmetic complexity. I should hasten to add that here we're always talking over fields of characteristic other than 2. Over fields characteristic 2, the permanent and determinant coincide completely. Unfortunately, we don't seem to be anywhere near being able to prove superpolynomial lower bounds of the permanent for general arithmetic circuits. However, some really interesting results have been proved in restricted cases. For example, we know that with respect to monotone arithmetic circuits, there's an exponential lower bound for the permanent. Similarly, with respect to depth 3 arithmetic circuits defined over finite fields, there's an exponential lower bound for the permanent. Unfortunately, these lower bounds, and indeed many lower bounds of this sort, also apply to the determinant, which is a little awkward considering we know that there are polynomial size circuits for the determinant. In this paper, we're going to be introducing this notion of a symmetric circuit, and in this model we do separate the permanent and the determinant. In particular, we prove a polynomial size upper bound on the determinant and a superpolynomial almost exponential lower bound on the permanent. At this point, I should talk about another application of symmetry in arithmetic complexity. Landsberg and Ryser introduced the notion of a symmetric determinantal representation. And in this model, they also separate the permanent from the determinant. However, the notion of symmetry they consider is quite different, and it's not entirely clear how we can translate lower bounds for this model to lower bounds for arithmetic circuits. As such, the results seem incomparable. Before we discuss symmetric circuits, we need to discuss symmetric polynomials. First, we should note that the permanent and determinant are not symmetric polynomials in the conventional sense. That is to say, they're not invariant under arbitrary permutations of their variables. But they do have certain natural symmetries that arise from the matrix structure. So let's begin by defining a more general notion of symmetry. Let's suppose we have some set of variables x and some group acting on that set of variables. There's a natural sense in which this action lifts to a ring of polynomials defined over x. And we say some polynomial in that ring is G-symmetric if every permutation in the group fixes the polynomial. In the same way, we can define a similar notion for functions of the following form. We consider the permanent to be a family of polynomials symmetric under row and column permutations. That is to say, we treat it as a G-symmetric polynomial where G is sim n cross sim n with the natural action of sim n cross sim n on the n by n matrix of variables xn. We consider the determinant as a family of polynomials that are symmetric under simultaneous row and column permutations, as well as under transpositions. We're now ready to introduce symmetric circuits. We say some circuit C computing a G-symmetric polynomial or function, depending on the context, is a symmetric circuit if the action of each permutation in G extends to an automorphism of the circuit. Let's consider an example. The input gates here are shown in green and are labeled by X, Y, and Z. The internal gates are in blue and the output gate is in red. And let's suppose we want to consider a permutation, the transposition XY, and think about how that might extend to an automorphism of the circuit. Well, the first thing we note is that the children of X and the children of Y need to be preserved. And so what we're going to have to do is map these two gates labeled here, shown here, to one another. So indeed, this circuit is symmetric under the group generated by the transposition XY. However, we could consider another transposition, YZ. And in this case, we notice that Z only has 2 children, Y has 3, so there's no way we're going to be able to extend this to an automorphism of the circuit. So this circuit is not symmetric under the action of the full symmetric group on X, Y, and Z. An important idea we're going to need later is the notion of an orbit. The orbit of a gate G is the set of all gates, pi G, where pi is some automorphism extending a permutation in G. At this point, I should note that a notion of symmetry has been considered for Boolean circuits before. In that context, the primary interest was in circuits computing graph properties or properties of relational structures, and the notion of symmetry was considerably more restrictive than the one introduced here. Let's now consider a concrete example. Ryser's formula gives perhaps the best known upper bound for computing the permanent for general arithmetic circuits. The formula is defined as follows. The obvious implementation of this formula yields a family of circuits of size 2 to the n times n squared. And it turns out this family is symmetric in exactly the sense we've just described. The main result of this talk will also give a lower bound that almost matches this upper bound. Let's now discuss the first major result of this talk, the upper bound for the determinant. In particular, I'll briefly sketch a proof of the following theorem. For any field f of characteristic 0, there exists a family of symmetric arithmetic circuits defined over f with the cubic size computing the determinant. And briefly, the idea is simply to apply Dawar's method. Now, let's recall the characteristic polynomial n by n matrix is given as follows, where that Pn at the end there is in fact the determinant of the matrix, n. Dawar's method gives a recurrence relation for each pi, and in particular then allows us to compute Pn, the determinant. Each Si is simply the trace of the ith power of the matrix M. So then we define a symmetric arithmetic circuit computing the determinant as follows. For each I, we first compute the ith power of the matrix M and sum over the diagonal to get the trace. We then recursively compute each pi using the recurrence relation given above and output Pn. It's easy to observe that this circuit will be symmetric. Unfortunately, Dawar's method necessitates the restriction to fields of characteristic 0. The recurrence relation requires dividing by I for each I from 2 to n. As such, we can't apply this method, at least obviously, to fields of positive characteristic. We now move on and discuss the main theorem of this section, the lower bound for the permanent. The main theorem is stated as follows. If f is some field with characteristic not equal to 2, then for every epsilon, there is no family of symmetric arithmetic circuits over f with size 2 to the n to the 1 minus epsilon computing the permanent. Indeed, it should be noted that over fields of characteristic equal to 2, the permanent is equal to the determinant, and we already have a polynomial upper bound in that case. So this is the best that, so we can't hope for a result of this sort when the characteristic is equal to 2. The approach we're going to take is going to rely crucially on a well-known observation, namely that the number of perfect matchings in a bipartite graph is equal to the permanent of the biadjacency matrix of that graph. We prove the main theorem in 2 steps. In the first step, we establish a translation from arithmetic circuits to Boolean circuits. So in particular, we show that if the permanent can be computed by a family of symmetric arithmetic circuits with some bound S on the orbits, on the size of the orbits that appear in that circuit, then the problem of checking if the number of perfect matchings in a bipartite graph is equal to some k can also be decided by a family of symmetric Boolean circuits with the same bound on the size of the orbits. And in this way, we translate this problem from a problem about arithmetic circuits to a problem about Boolean circuits. We then show that there's an almost exponential lower bound on the size of the orbits of a family of symmetric circuits that decide this problem. So we establish the lower bound in the Boolean case. And here we use an already established connection between lower bounds for symmetric Boolean circuits and Weisfeiler-Lehmann dimension, as well as a novel counting argument for counting the number of perfect matchings in a bipartite graph. Let's now deal with the first step in this proof, the translation from arithmetic circuits to Boolean circuits. So in particular, to prove the first step, we need to prove the following theorem. Let phi be an arithmetic circuit over some field with variables x, computing a g-symmetric function, and k be some element of the field. Then there exists a symmetric Boolean circuit C with threshold gates, also computing a g-symmetric function. And what C does is for an arbitrary 0-1 assignment to the variables x, it checks whether the polynomial defined by phi will evaluate to k. Right? So it outputs 1 if and only if that polynomial evaluates to k. Now, this circuit could be exponentially larger, so the circuit C could be exponentially larger than the circuit phi, but the construction is such that the circuit C and phi always have the same sized orbits. The full proof of this theorem is a little bit technical, but I'll sketch out the overall idea here. We first observe that for every gate G in the arithmetic circuit, there are only a finite number of values G could evaluate to if you assign the input variables to 0 or 1. We then recursively construct the circuit C by replacing each gate G in the arithmetic circuit phi with a Boolean circuit CG that has an output gate GQ for every Q in AG. In other words, it has an output gate GQ for every possible value G could take on for a 0-1 assignment to the input variables. The idea is that GQ evaluates to 1 for a given assignment to the input variables, if and only if G would have evaluated to Q. Lastly, if H is the output gate of phi, we take HK to be the output gate of C. And if K was not a possible value that H could have taken on, well, then we just set C to be the always 0 gate, which is trivially symmetric. Before we move on and discuss the lower bound for symmetric Boolean circuits, we should first review some important concepts from the literature. For a natural number k, the k-dimensional Weisfeiler-Lehmann equivalence is an equivalence relation on graphs that over-approximates isomorphism, in the sense that if two graphs are isomorphic, then they're definitely k-dimensional Weisfeiler-Lehmann equivalent. Moreover, for increasing k, this relation gets finer and finer and finer. And once k gets larger than n, the size of the graphs, the two graphs are certainly isomorphic. Importantly, it was shown by Seyfior and Immermann that there's no fixed k for which the k-dimensional Weisfeiler-Lehmann equivalence corresponds with isomorphism. A graph parameter is an isomorphism invariant function from the class of all graphs to the natural numbers. Standard examples include the chromatic number of a graph, the number of perfect matchings, the number of connected components. For a given graph parameter mu, the counting width of mu is a function nu such that nu n is the smallest k, such that mu is invariant under k-dimensional Weisfeiler-Lehmann equivalences on graphs of size n. The counting width of a class of graphs is the counting width of its indicator function. There are numerous results establishing the counting width of a number of graph classes and graph parameters. And we know, for example, that the classical Hamiltonian graphs has unbounded counting width, and that the graph parameter that determines the number of 3 colorings the graph has unbounded counting width. Moreover, there are classes with bounded counting width. For example, the graph parameter that determines the number of connected components a graph has bounded counting width, as does the classical graphs with a perfect matching. We now move on and prove the second step in our lower bound for the permanent. Here we use a result by Anderson and Dawar that establishes that so long as a class of graphs can be decided by a family of symmetric Boolean circuits with a bound on the orbit size, then there's a corresponding bound on the width of that class, on the counting width of that class of graphs. This means that we can prove lower bounds for for the orbit sizes by proving that the counting width is unbounded. So, in this particular case, let's let mu0 be the graph parameter that denotes the number of perfect matchings in a given graph. And mu p for some prime p be the residue of mu0 modulo p. To complete the proof of the main theorem, it suffices to prove a linear lower bound on the counting width of the graph parameter mu c for some c either 0 or an odd prime. We do this by establishing that for every k, there's a pair of balanced bipartite graphs, x and y, that have at least k vertices, that have at most k vertices, such that x and y are k equivalent, but the difference between the number of perfect matchings in each graph differs by a power of 2. The rest of this talk is dedicated to proving this linear lower bound on counting. So now we need to show for every k that there exists a pair of graphs that are k-dimensional bispecific equivalent, but which have a number of perfect matchings that differ by a power of 2. And what we use to do that is a variation on the famous CFI Construction construction. So we're now going to briefly discuss this construction. Let G be a 3 regular 2-connected graph, and let XG be formed from G by replacing every vertex with the gadget picture on the right, and we call this the even graph. Notice that this graph has 4 internal vertices, one for each even subset of the set of all edges incident on G. One vertex VB, which we call the valence vertex, and for each edge it has 2 vertices. So the edge F incident on V becomes F0 and F1. We define the graph x tilde G similarly by replacing each vertex with the same gadget seen on the right, except in this case we specify one vertex, which we call the special vertex, and at that vertex, instead of replacing that vertex with the gadget seen on the right, we replace it with a twisted version of the gadget. I won't go into details into how that's constructed. We call this graph, x tilde G, the odd graph. We let IV be the set of internal vertices in the gadget. Those are the ones colored in orange on the right. We note that by a standard expanded graph construction, we have for every k a suitable graph G such that xg and x tilde G, the odd and even graphs, are k-dimensional bispecific equivalent. We now develop a few concepts that we'll ultimately use to count the number of perfect matchings in the odd and even graphs. We now divide the perfect matchings into 2 types, either uniform or non-uniform. Let X be either the odd or even graph, and consider some perfect matching M in X. We say M is uniform if for every vertex V and every incident edge E, there's exactly one edge from E0, E1 to an internal vertex in M. This is perhaps made most clear if we look at the diagram on the right, and we can see that there's exactly one edge from G1 and G0 to the internal vertices, one edge from F0 and F1 to the internal vertices, and one edge from H1 and H0 to the internal vertices. If a matching is not uniform, we say it's non-uniform, and very importantly, we can show with not too much difficulty that the odd and even graphs have exactly the same number of non-uniform matchings. And as such, all that remains is to count the number of uniform perfect matchings in each graph. In order to count the number of perfect matchings in either the odd or even graph, we consider orientations on G. An orientation on G is simply a directed graph formed by picking a direction for each edge. A uniform perfect matching of either the odd or even graph induces an orientation of G, which we call GM, by picking for each edge, EV, the direction U goes to V, if M contains an edge between E0 and IU, and an edge between E1 and IV. In other words, exactly as pictured on the right-hand side. It's possible to show that every orientation arises from some perfect matching, which means that we can count the total number of uniform matchings by counting the total number of orientations, and for each orientation, counting the number of distinct uniform perfect matchings that induce it. We now use the approach just described to show that the number of uniform perfect matchings in the odd and even graph differ by a power of 2. Let X be either the odd or even graph, and now we fix some orientation of G, arrow G. And the idea is we want to construct all the perfect matchings that induce arrow G by independently choosing appropriate perfect matchings from each gadget and then combining them into a single uniform matching. The key question there is, what are the appropriate perfect matchings that we could pick at each gadget in order to build this global uniform perfect matching? By considering the uniformity constraint and the fact that the perfect matching must induce an orientation, it's easy to see that the perfect matchings we're looking for on gadgets must contain precisely one edge from each pair E0, E1 to an internal vertex in the gadget, and which we're picking, whether it's E0 or E1, must depend on the direction of the orientation of E in arrow G. It's possible to show that all these appropriate perfect matchings at each gadget are either all contained in a gadget isomorphic to the graph T, shown on the top right, or all contained in a graph isomorphic to the graph S, shown on the bottom right. We say that the vertex V is a T vertex in X in the first case, and we say that it's an S vertex in X in the second. But, importantly, these two graphs have a different number of perfect matchings. The S graph has 4, and here we can see them, 1, 2, 3, 4, and the T graph has 2, 1, 2. Moreover, if we pick some vertex V that we know is not the special vertex, then V is a T vertex in the even graph if and only if it's a T vertex in the odd graph. However, if V is the special vertex, then it's a T vertex in the even graph if and only if it's an S vertex in the odd graph. The result is here we get a different number of perfect matchings. And when we combine these perfect matchings at each gadget, we get 4 choices in one case and 2 choices in the other. And as such, with a little bit of combinatorial work, we can show that the number of uniform perfect matchings in the even graph differs from the number of uniform perfect matchings in the odd graph by a power of 2. This completes the proof of our main theorem. So to conclude, we've developed a natural notion of a symmetric arithmetic circuit and shown that there's a polynomial upper bound for the determinant in this model and an almost exponential lower bound for the permanent in this model. There are a number of interesting questions that remain open. Firstly, the upper bound for the determinant we prove only holds for fields of characteristic 0. It's natural to ask whether Lever's method or perhaps some other method might be adapted to prove the result for fields of positive characteristic. Another natural question to ask would be to consider the upper and lower bound proof for the permanent and determinant if we vary the group with respect to which these polynomials are symmetric. In the case of the permanent, we could consider smaller groups and perhaps as a starting point, the group consisting of all simultaneous row column permutations. In the case of the determinant, can we prove the upper bound for larger symmetry groups, and in particular, perhaps for the full symmetry group of the determinant? It would be interesting to consider possibly improving the lower bound for the permanent, with the hope of perhaps proving a lower bound for the permanent that matches the upper bound for the permanent for symmetric circuits offered by Ryser's formula. Thank you so much. That's the end of the talk. I hope you had a good time. Thank you so much for listening.